Hi, today we will present our medical imaging final project, enhancing MRI image quality through wavelet-based multiscale denoising. My name is Mehmet Salih and I will present our introduction part. Here is can you see our dataset. Our study uses the Ohio State Cardiac MRI raw data, which is publicly available and detailed in OCMR dataset. This dataset includes raw case-space data collected from cardiac MRI scans, providing a rich source for analyzing image quality under various conditions. Here is you can see our basic pipeline. Let's go through how we process MRI data in our project. We start with case-space data, which is the raw data from the MRI scan. First, we add additive white Gaussian noise separately to both the real and imaginary parts of this data. We do this to better simulate the real-life conditions of MRI data collection, where noise can affect each part differently. Then we use a technique called 2D discrete wavelet transform. This method breaks down the noise data into different frequency and resolution components. The 2D discrete wavelet transform is mainly utilized for image and video processing, which is the key part in multiscale denoising. Similar to 1D discrete wavelet transform, 2D discrete wavelet transform decomposes an image into various subbands having different resolutions and frequencies. However, unlike 1D version, here the discrete wavelet transform operation is performed by applying it separately along the rows and columns of 2D data, so that four subbands arise corresponding for each level of decomposition. Uh, there are the approximation subband, the three detail subbands representing horizontal, vertical, and diagonal high frequency components, respectively. By iterating this process on the approximation subband, similar to the figure 3, a multi-level decomposition is achieved. Next, we apply something called thresholding to the wavelet transformed data. This is where the tweaked data a bit, reducing the tiny details that are probably just noise, while keeping the big important details that represent crucial parts of the image. We use two methods there, soft thresholding, which gently reduces noise levels, and hard thresholding, which cuts off the smaller details more abruptly. As you can see, the image illustrates three types of signal thresholding techniques: the original signal, hard thresholded signal, and soft thresholded signal. In the hard thresholding, middle graph values below a certain threshold are set to zero, creating a step-like appearance where the signal abruptly transitions between zero and non-zero values. Soft thresholding, right at the rightmost graph, in contrast, not only sets values below a threshold to zero, but also shrinks values above the threshold, resulting in a more gradual transition and smoother signal output. Let's continue to our pipeline. When we clean up the data through thresholding, we run an inverse discrete wavelet transform. This is basically reverses the initial wavelet transform, putting all the data pieces back together to reconstruct a cleaner version of our original case-based data. And finally, we take this cleanup case-based data and reconstruct it into an actual image using a method called a sum of squares. This technique combines signals from different MRI coil data, and that's how we enhance MRI images in our project, making them clearer and more useful for medical professionals.
Hello everyone, I am Ayberk and today I will be presenting you our MATLAB code regarding enhancing MRI case-based data under different SNR conditions utilizing various wavelet functions and threshold values. Here you can see the wavelet basis functions that we have utilized. However, due to time limitations, while giving you the third demonstration of our code, I will be showing you only two of them, namely the OpenHS 8 wavelet basis functions and Bayer 4.4 wavelet basis function. Here you can see our main wavelet denoising code, which will be explained in a very short time in a detailed manner. So let's continue with our MATLAB code. Here you can see the MATLAB code. So let me initially run the code. Here, initially we select our OCMR data that we utilized. And here you can see our reconstructed image with the case space data for representing one of the coils. We have reconstructed the image using the sum of squares method. Secondly, we again select the same data and add some noise to the data, namely AWGN noise. Here again, you can see the noisy reconstructed image and the noisy case space data, one of the coils for the noisy case space data, for which this is literally zero. And thirdly, we will be using denoising, wavelet-based denoising methods. To do this method, we utilize the wavelet denoising function. As my friends previously indicated, we initially at zero padding, and then we take the discrete wavelet transform of the code, apply thresholding, take inverse discrete wavelet transform, and remove the paddings so that we achieve a denoised case-based data. After achieving the denoised case-based data, we simply reconstruct the image. Here you can see the denoised reconstructed image and denoised case-based data. As you can see in the SNR metric, the SNR was before minus 6.4, and here we achieved 10.83 dB SNR. Later, we utilized the built-in MATLAB function to do wavelet denoising. Checking the SNR values, actually we achieve a higher SNR than the previous one. However, if you were to analyze the image, you could see that for the wavelet-based denoising method, we achieve actually artifact here, which is not wanted. After that, we actually have some codes regarding our report so that we could visualize some of the basis functions and also achieve a visualization for the threshold values.
Hello, I'm Ozan Oğuztuzun, and I'm going to be presenting you our project results, and then I'm going to be discussing the experiments outcomes. So here you can see the general flow of our experiments. We used three different noise levels, 0.1, 0.5, and 1 SNR. For all wavelet functions that we used for denoising. Here you can see the original reconstructed image when it is added noise. And then, for example, by using DB8, RBIO 3.9, or HAAR base functions, we can denoise this noisy image and get a reconstructed denoised image, but each wavelet function gives us a different result, and we tried 7 of them in total using different noise levels and got our results. Here we compared each wavelet basis by how much the SNR value changed, and we tested each wavelet basis with hard and soft filter settings. We can also see that the smoother wavelet bases such as BIOR 4.4 and DB8 consistently delivered superior results, particularly under hard thresholding, due to their ability to effectively capture low-frequency components and retain their structural details. And in contrast, wavelets like RBIO 3.9 struggled with limited SNR improvements, especially with hard thresholding. And interestingly, the impact of the initial noise level varied. For lower SNRs like 0.1, soft thresholding provided more stable improvements across all wavelet bases. However, as the initial SNR increased to 1, the performance gap between soft and hard thresholding narrowed for smoother wavelets such as DB8 and BL10. These are our references, and thank you for listening.